Alright, hit the button. Yes, draft physics type video on photons, first edition, I suppose. Trying to just consolidate some of these points and arguments and make it easy for anyone who cares to make some sort of counter proposal about how there's some critical evidence that makes something of what I'm going to describe incorrect or wrong-headed or provably wrong or something like that. So, photons. Yes, volume 1. The Wikipedia page just doesn't say much. I mean, there's a lot of writing, but it doesn't say much about exactly what a photon is, or how exactly it functions, or what exactly it sort of looks like. Beyond the same stuff they've been showing for 50 years, there's just nothing really new. They have a bunch of new ways of describing things. It's bosonic, and they actually do give it a charge of some kind and some sort of mass in a strange way, as a moving object versus a object not moving, a rest mass. So this is all. It's all basically just a way of, they put it all in their own language, their own keywords or key concepts, and so you have to accept all of their key concepts for any of this, these descriptors to have any meaning. So I could call it like the Pinocchio factor, and how much leprechaunness it has, and how much fairy dust, because these are all concepts built, as premises in describing all of physics now. It's all shoved into the standard model kind of rhetoric. And you have to assume that somehow that those foundational concepts of leprechaunness is actually meaningful, like it's actually a real thing, leprechaunness. And I would argue it's probably not. Some of it might be valid, but most of it, like ideas of spin, they give it a spin of 1, which essentially could be interpreted as saying it flies in a straight line. Things with a spin 1 would be things that go straight. Things with some other spin are things that go crooked. Something like that. But you have to always say something like that, because you can't really understand exactly what they're talking about. So anyway, maybe I will just read a little bit of this and you just get the idea that it's all kind of vague as a concept, and I'll just go through how I looked at it throughout my life and what it seems to me that these words actually mean. Okay, so a photon is a type of elementary particle. Interesting. The quantum of the electromagnetic field. So they're calling it essentially the element of the field, I guess. So the field, the electromagnetic field, is made of photons. Photons moving and not moving. I mean, if the field is not doing anything in particular, I guess you would say it's full of photons that aren't moving, I guess. Including electromagnetic radiation, such as light, and the force carrier for the electromagnetic force. So the force carrier just means basically the thing that actually is transmitting the energy, but then they go on to say, in parentheses, even when static via virtual particles. So I don't even know what that exactly means, even when static via virtual particles. They mean static electricity? This doesn't really tell you much. The photon has 0 rest mass. Well, that's just so helpful. And always moves at the speed of light within a vacuum. I would argue it always moves the speed of light, and the only thing that changes its speed is the changes in its direction. It travels more distance, it'll move slower. Take longer, because it's traveling more distance through mediums. But that's not even a conversation that it's touched on here at all. So we're just left with this idea that it's Oh yes, well, it always goes a constant speed in a constant medium. So if you put it in a vacuum, it's a constant speed in the vacuum all the time, and if I put it in water, it's a constant speed in water all the time, blah 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 blah, something like that. Alright, like all elementary particles, again, particle, photons are currently best explained by quantum mechanics, as if quantum mechanics was a thing, you know, as if quantum mechanics was something rigidly described and defined, and that you could go to the dictionary and you could, like it was solid, like all the physicists knew what quantum mechanics meant. When you say the word quantum mechanics, the exact same images and pictures would pop into everybody's brain. There's no such thing as quantum mechanics. There's Heisenberg and Huygens and wave theories and Maxwell's ether, and there's all kinds of stuff that is quantum mechanics. Anyway, and exhibit wave-particle duality, which again is supposed to be a thing. To me, that's like saying it has leprechaunness. You know, you know, nothing else in the universe has this duality problem except these photon-y things. Anyway, exhibiting properties of both waves and particles. And again, so saying that the photon actually exhibits this property, when no, what exhibits the property are experiments, and you can conclude that the appearance of the outcome of the experiment, you can blame it on the particle, the photon, or you can blame it on the obstacle course you ran the photon through. But there's no distinctions made there, of course. So again, it's this idea that no, it has nothing to do with the obstacle course, it has to do with the photons. It's a property they have. You know, again, which to me is it's very presumptuous. It's a conclusion reached way too soon and way too firmly stated. For example, a single photon may be refracted by a lens and exhibit wave interference with itself. So it actually say those words. You're just, okay, and how do you explain that? How do I image this wave of electromagnetism that isn't supposed to spread but is now spreading, interfering with itself? I mean, the field of photons is somehow disrupted by one photon, and it moves all the photons, and then all the photons in the field interfere with each other, and then just one photon hits the target. Something like that. But again, no images to go with the fluffy talk. With itself, and can behave as a particle with definite and finite measurable position and momentum, though not both at the same time. So they qualified it, meaning that the measurement can't be at the same time. Careful language maybe, but you know, still kind of leaving this kind of notion that somehow it doesn't have a fixed position in time and space, but qualifying it with this word measurable. The photon's wave and quanta qualities are two observable aspects of a single phenomenon. The photon's wave and quanta qualities. So the fact that it's should have said particle qualities rather than quanta. But anyway, so the photon's wave and particle qualities are two observable aspects of a single phenomena. You know, but they have to be observed independently. And you'll never see them at exactly the same time. So the photon is, it's like just saying the photon is waving or particling, and we don't know exactly which one or why it's doing either one. Anyway, it cannot be described by a mechanical model. So that's, you know, a bold statement. Cannot be described by a mechanical model. How do they know it cannot be? You mean forever and ever? It'll never be able to be described in a mechanical way because they've thought of all possible compositions of a mechanical model. They've done them all. They figured out that you could ever make a three-wheeled car or something. You know, can. Anyway, a representation of this dual property of light, which assumes certain points on the wavefront to be the seat of the energy. So we have a driver, a little energy driver, and then we have the mechanism of the photon surrounding, protecting its little energy kernel, or some kind of, I don't know. It's no, like I said, it's just left to your imagination to make this up. Is not possible. So, which assumes certain points on the wavefront to be the seat of the energy, is not possible. Again, these declarations about what's possible, as if, like I said, they have so thoroughly analyzed and modeled. And there's no examples of models here. Not one single example. Not a Newton model, not anyone's model. The quanta in the light wave cannot be spectrally localized. I think it can be. Some defined physical parameters of the photon are listed, and those are on the right. Quite useless, actually. The modern concept of the photon was developed gradually by Albert Einstein. I think that's debatable, but whatever. I mean, I think he sort of protested a lot of where the design went in the early 20th century to explain experimental observations that did not fit the classical wave model of light. So again, classical physics at 1 minute is Newtonian, and the next minute classical is wave. Now Newton wasn't a wave guy. Huygens was the wave guy. And so there's, this is just this rhetoric that you're allowed to use these words, to describe classical. When you use them, you use the word classical to describe two entirely different philosophical or even just scientific points of view. It's like saying religion and a God theory and evolution, and calling them both classical. I mean, it just doesn't make any sense. The benefit of the photon model was that it accounted for the frequency dependency of light's energy. So that's an assumption that was made based on the fact that, as I've explained, because firing photons at certain frequencies can create different physical effects. That is, how fast you do something can affect the product. Now, there's probably lots of examples of this, but I just use tipping point as an example. That, if you hit something, throw a baseball at something once, and then while it tips back, you hit it again. So it's like a boxer would understand this. You throw one punch and it gets the guy leaning, okay, and if you can get that second punch in while he's still leaning, you can knock him down, that kind of thing. And because there's an effect like that, the assumption is that somehow frequency imparts more energy, and it doesn't. It just has a circumstantial advantage. There's a circumstantial advantage, if you want to knock something over, of hitting it at certain speeds that would be within the harmonic. So it's like pushing a pendulum. If the pendulum's over here and I push, nothing's going to happen. It's useless. It's no energy. But if I push when the pendulum's coming right at me, I'm not going to do much either to make the pendulum go faster or higher. But if I push when it's coming on its downstroke, it'll have a completely different effect. So depending on when I push, can have a huge impact on whether the energy is fully realized in terms of a physical effect on the world. So I'd say that's just right there's a point I'm making. That's a prediction. That's a wrong assumption. Just like Einstein's assumption that a mass moving, if it starts going really, really fast, that somehow it gets too heavy to push. Like somehow its mass increases, and that's why you can't push it anymore. And I would argue exactly the opposite is happening, because the stuff inside of it is all moving so fast. Most of it's going the speed of light in the direction. You can't push it with anything. There's no parts that aren't going the speed of light, so you can't make a pusher that goes faster than the speed of light, so you You can't push something that's going almost the speed of light. So it has nothing to do with its mass increasing. It has to do with the fact that its mass is totally evading you. There's no mass to hit. It's becoming one-dimensional, and it's moving the speed of light in that dimension, and you can't push something one-dimensional moving the speed of light in that dimension. So, so I don't know if I need to, I don't even know where I left off, but let's see. We did the lens thing, seat of the energy, the modern concept down here, frequency dependency of light's energy, and explain the ability of matter and electromagnetic radiation. So they use the words electromagnetic radiation, which is the same thing as a photon. Now in this context, to be in thermal equilibrium. Now who knows what they mean by that, but I think the real point would be is their equilibrium. They're really, what they're saying by thermal equilibrium is you can't break pieces off of a photon. The photon model accounted for anomalous observations, including the properties of the black body radiation, and others, notably Max Planck, had tried to explain using semi-classical models. So we don't even know what semi-classical means. We're back to wave theory again. So that's the joke here, is the classical in this article means wave theory, where classical and most of the people that use the term means Newton, which means particle. So there's just no consistency in the use of these words. In that model, light was described by Maxwell's equations. And so again, Maxwell was a wave guy because he was an ether guy. But Maxwell's equations don't have any, they're not dependent on waves. They're just dependent on vectors. There's no interference in Maxwell's equations, essentially. Well, that's not true. Well, it sort of is. I mean, Maxwell's equations don't have any, don't give implicit properties to the virtual tons. They're not even tons in Maxwell's theory. They're just an effect. So the force carriers aren't even identified in Maxwell's equations. Just the effect is identified. Alright, but material objects emitted and absorb light in quantized amounts, i.e. they change energy only in certain particular discrete amounts. And so this is, I think this is, yes, it's demonstrated by lots of ways. I don't know if I would use black body as a way of describing that, because the black body radiation thing has more to do with the more complex elements of photons and the fact that they don't create infinitely high frequencies in common interactions. It takes a very extraordinary interaction to create very high frequencies. So there's not a straight line kind of curve of the ease with which you can create photons at the different frequencies. They're much easier to create at the long frequencies, the long wavelengths, than they are to create at the high wavelengths, because the high wavelengths are essentially a representation, a consequence, a byproduct of extremely high pressures, and I'll explain that. Alright, so that's probably enough of a blah blah blah, but there's nothing in the article that actually does anything valuable in terms of, they do have this funny drawing of space and time as if this has something to do with photons, which I'd say that's all made up rubbish. And some talk about polarization, but very little. They don't even have a good diagram of the two waves superimposed on each other. It's kind of a, it's just kind of a funnily less descriptive than many diagrams. This won't be, that's just the moving an electron from different energy levels and ending up releasing a photon, but no real explanation of how that happens. The little animation here was kind of useless. It's a certain kind of an interferometer and they have photons that are seen and unseen, which I think is kind of bogus. But anyway, so anyway, it's a they have lots of stuff, but nothing that shows any kind of model of what a photon could possibly be as a mechanical entity. Just no conversation whatsoever about how its energy or its frequency could be understood. So I'll do some of that and then throw in the background of where photons come from. So nothing in the article explains how a photon is created. They just say that these circumstances will cause a photon to be released, but there's absolutely no description of where it's released from, how it's released, and what mechanism creates a photon out of how matter synthesizes one of these things and produces it. And certainly nothing about the mechanics of where a virtual photon would come from. And let's understand that the virtual photons don't, like magnetism, don't come in a form that we can see in any way, but indirectly, by how it affects a piece of matter. Where with light, at least we have some connection to it, in that we can actually process that force directly with our eye. So it gives us some indication of its substance. And clearly radio waves we don't have that same connection to, because especially as a photon, because we can't see it. Can't have one hit us and say, oh yeah, I get that, it hit me. Flew into my eye. We don't have a radio wave detector. I guess even if we did, it's like with sound, you really don't get any kind of idea of how you're processing sound. Your ear sees it, but you don't have the same vision for sound that you have for your eyesight. It's not as panoramic. You don't see sound in a context where you see photons in a context of photons, and you don't see sound that way. Every sound is kind of like in a darkness. It's always isolated, and so there's no perspective, where light sort of gives you this three-dimensional perspective. You don't have three-dimensional kind of hearing, where you can get that kind of perspective. Alright, I think that's enough of their crap. Just pointing out that it's crap. I mean, it's not, it might be perfectly satisfactory jibber-jabber, but I just mean as an explanation for what a photon is, it doesn't enlighten you at all. It doesn't give you any clue of what the hell's going on and how this stuff works. So we'll go to the drawing table, hopefully, and see what we can do here. So when I was first introduced to the concept of photons, it seemed perfectly sensible that they would be things. All right, so it was always explained as it's a thing. It's called a photon. So that's sort of a step that Einstein did. Was other people had sort of vaguely labeled this thing, and Einstein reinforced the label of a thing, a little corpuscle, a lump of something, with a lump of energy. And so at least it had some sort of narrowness to it, and it was sort of clear, I think, that part of it. But what wasn't explained, I mean, we don't have any like Einstein drawings of what he thought a photon might have looked like. So what we know is it has a frequency, but that doesn't tell you much. So you could think of a frequency as being very, very long photons and very little breaks, or you could think of a frequency like this would be 1 ton, one photon, and you could think of it as having a front end and a back end to define the frequency, something like that. Or you can model it as the ton just being something separated by a distance, that it wouldn't have to have any thickness at all, zero almost, and that it would just be this piece of energy, separated by a distance, which would be the frequency or the wavelength. So it would be an on and off. And that's sort of what Einstein is saying, and the other experiments are basically saying is that photons have a quantity of energy, an on and an off. They don't have a coming on, going almost all the way on, coming down. So this traditional notion of describing either one of these two physical particle models, okay, particle model versus some wave model. The problem with the wave is this is already in trouble because there's no evidence that you could get this much energy out of a photon, or some other point on a wave. It wouldn't, there's no clump here. So wave implies that photons come at you and there's a little bit of the photon hits you and a little bit more and more, and then you have a peak, and then it goes no photon, a little less photon, less, and then you have a peak at the so you have these peak points. But there's no evidence that photons do that, and the evidence is exactly the opposite, that no, they either are all the way on or they're all the way off. There's no wave. There's no graduation to the energy. It's all or nothing. So, wave is already in a little bit of trouble just when you're starting off your model, because there's nothing in the evidence that indicates they are gradually doing anything, that they're in any other position other than I'm here or I'm not here. I mean, that's clearly what, and the irony is, quantum mechanics, which is really saying it's a quantity, isn't really quantity mechanics. It's this not so much quantity. It's this vague quantity, this not quite. So again, the sine waves could represent time, and you could say, you could perhaps draw it as a position. Photon is here and then it moves through time, and you still can't make a sine wave out of the movement through time, so it still doesn't make any sense to me personally. So this here is obviously the model I choose to defend as being the sensible one. The photon is just bits of quanta. You can call them a particle, I don't care, or you can just call it a force bit, a thing. Whether it's made out of, who cares what it's made out of, right? It can be made out of jello, it could be made out of fudge, it could be made out of peanuts. Who cares? The point is that it has the capacity, when it goes and hits something, to impart its energy, in a sense, to stick to it and go with it. It's a fish, let's say, to use a simple metaphor. There's a school of fishes that you can call matter, and there's the individual fishes. And the photon is essentially an individual fish that can go into a school of fish, into an atom, and it changes the atom while it's in there. Gives it a certain amount of attitude, and if it leaves, then it's done being changed by that photon, and now that photon, that fish, can go off to another school and mess with it for a little while, or it can go through another school, but the fish never dies, and it has an effect. Now the trick is that my argument is this is what they're calling a fish, is this frequency. See, we can see these things at a frequency, and we call them, so we put energy when it's at a frequency that we can detect, this quanta of energy. This isn't virtual yet. See, I would argue the virtual photons are just these little bits at a frequency that's not detectable. That is, they're not traveling to the same exact location on a path. Instead, they're coming in a scattered manner that doesn't provide any consistent frequency, so you can't detect them because they don't do the tipping point thing. They don't hit the same place in a row, so they can't be detected because they can't tip, except very rarely randomly. So every now and then, the scattering, like I could scatter bullets, just wave a gun and shoot bullets, And it could be true that in doing that, 2 bullets hit exactly the same location, and that would be a photon. But the scattered ones would be invisible because they don't have a frequency. So you have to understand that the entire electromagnetic radiation spectrum is, oh, can't see that. Yeah, well, whatever. Electromagnetic spectrum is just stuff at a frequency. We identify it based on its frequency, how often they come. And we produce them very differently. Like light, we don't make a light's, photons. We don't give them their frequency. We excite matter and have the matter produce the frequency automatically of red light or blue light or green light. And the same is true with X-rays and the rest of that stuff. But for like radio waves, we actually produce the frequency. We actually shoot the tons by creating a vibration that's on and then it's off, and it's on and then it's off. So it's making photons and it's not making photons. So the argument would be a simple one. It's a radio tower. When it, you use this symbol of the radio waves coming off of it, it's not producing waves. It's producing a bunch of photons, a bunch of these little bits, and then a bunch of little bits, and then a bunch of little bits. So as the antenna vibrates, it throws the little bits as it vibrates. So the bits coming off on this side would have half the it would have a phase difference than the bits going off this way. It seems kind of obvious. It would take time for this thing to swing back and forth, so to speak. If you make it just simple, if you just make the argument that let's reduce what's happening to an antenna to something simple. Now it's not that simple, in that the electricity goes through the antenna both ways. It isn't really swinging it. So if you're using a swinging argument, yes, you can understand that the stuff going out one side would be exactly the opposite phase, because it takes time for you to wiggle it back and forth. But electricity isn't really doing that. We're shoving a bunch of electrons into it, into the antenna, and the antenna's reaction to that is to shoot a bunch of photons, a bunch of quanta, a bunch of these little cues. So again, this is sort of the irony of the conversation, is that they use a word like quantum mechanics, which, to me would seem, yes, that's exactly how it works. There's all these little bits. But they don't mean little bits. Quantum mechanics really doesn't have anything to do with little bits. So it's like Einstein's vision of quantum mechanics, or even Newton's vision of these reducible particles, and that you can get to some kind of idea of a checkerboard, and that the whole universe is really just being run, based on what these little bits are doing, where they are, and how they're interacting. But they're all standard. There's standard checkers and a standard board that they're interacting on. And models of photons can do that. You can make a model that fits that, in spite of what the Wikipedia page says in terms of no particle model can't do that. Yes, it can. And they just don't want that to be the truth, or they've written a whole bunch of books and dictionaries and they don't want to have to rewrite them. Maybe they just don't want to have to start over, because that's a lot of work. And they have to throw out all this stuff they've invested in. They have a car that runs on a fuel, and it's like you're saying, well, we got this new kind of fuel now that's better, more efficient, and they're like, well, my car runs on that old stuff. I don't want to do this new stuff. That kind of thing. All right, so the trick is that you would say, okay, well, why didn't they figure out that photons have this half quality? That they have a half amount of energy, in the sense that there's really 2 bits to everything we measure as a photon. There has to be at least 2 of the quanta, or we can't see the frequency. There's no frequency if there's no second bullet coming. And why didn't they figure that out? Well, they didn't figure it out because it's such a small amount of energy that we can't really tell the difference between 2 or 3 or 4. It's a tiny fraction. It's the smallest thing in the universe, and there's no measurement tool that can measure the smallest things. So even to measure photons, to actually detect them. We actually have to measure them moving electrons. So you can sort of understand that we're already requiring there to be a certain amount of energy, enough to move electrons. And if it doesn't move an electron, you don't see it. You can't register its existence. It could hit the electron, but if it doesn't move it in a significant way, thereby creating a cascade of other electrons moving, amplifying the effect, we can't see it. So we have to create amplifiers out of things much bigger than photons themselves. And so that's why what scientists call a photon might actually be 4, of things coming at that frequency. It might take 4 hits to tip the electron, to knock it. And that would be the minimum amount of energy we can detect. We need it to knock, and it might just take 4 of those hits for it to knock, and so that's what we call a photon. But it might be, in quanta terms, 4 of those things. All right. Yeah. So that's why there's no way to, you can only view these models in very, very indirect ways, and you can only see the photons in very, very indirect ways, measure them. And so that's why this is really hard for other people to model, is because we have these different pieces of evidence. You have this effect that happens with a 2-slit experiment, or you have this effect that happens when you're shooting electrons at a piece of metal and trying to get electrons free. And the two don't match in any real way in terms of the evidence they're providing of what the photons are doing, because in one case you're well, okay, I don't even get into the. In both cases, I think they wrongly assumed the function, in the sense that to release the electron, it's just a matter of not how fast the photons are coming technically. I mean, not the energy. There's no built-in energy. So I guess my point is that you can sort of understand that if we had 3 photons and 3 photons at 2 different frequencies, that this would be the same amount of bullets. It's the same amount of energy. The gun fired, there's no extra energy put into them. They're all just bullets. But you could see, just looking at it, that, well, if you were doing a timed equation, you could fit more of these closer ones together in the same amount of time than you could fit ones going at a bigger frequency. So you can see some obvious differences. But frequency doesn't make something more energetic in and of itself. So they've assumed that energy has something to do with frequency. And that only has something to do with frequency in terms of an effect on matter. It doesn't have anything to do with the fundamentals of how much energy there is. It just has to do with, it looks like more energy when you knock the pen down. So when the pen's knocked down, that looks like a lot of energy. But there's the same amount when the pen's going like this and when the pen actually falls down. If you hit it with the same number, it's the same exact amount of energy. It's just that if you do it in sequence, that is, you hit it at just the right moments, you knock the pen down. So it's just circumstantial. It's not intrinsic or fundamental to the photon. But now they have a whole theory. All of quantum mechanics, all of the standard model, is built on this notion that frequency is energy. And it's really not, unless you have the circumstance of the internal mechanism. So I guess that's the part to get to now. New piece of paper maybe is necessary. Alright, so what is a photon? What generates it? And so I have done some work on this in the past and explained it, but I'll try not to do it, well, I don't know, try to do it in a new way, but in the same way. I'm arguing that photons are something that's in atoms all the time, but they're in the atom in the form of just the bits. So they're not really, it's just the atom has a bunch of these little force bits, and the force bits move the speed of light. So you probably can't read that, but anyway, so force bit, F bit, and those bits are the same bits that gravity's made out of, the same bits that magnetism is made out of, and they're inside the atom doing the nuclear forces all the time. So they're those little bits create tension inside of atoms. So if we reduce an atom to the simplest form, the idea of a proton and an electron, two things with opposite charge, okay? And we just say a neutron is some combination that's likely spinning, and they're closer together. So that might be your neutron. It's made out of these two elements. It's just that it has both of them, and it has a neutral charge just because of the fact that it has both charges. So that's why it's measured as neutral. But anyway, so the electron, the proton, and then you have these bits. And the bits are actually in two forms of polarization. So they, square and round, however you want to look at that. And depending on how, which color is hitting, the relationship to each other is that the little blue bits bounce off of blue things, and the red bits bounce off of red things. But if you hit a blue thing with a red thing, it leaves perpendicularly. And if you hit a red thing with a blue thing, it leaves perpendicularly. So so this becomes a valve in a sense, where all the pressure can leak out. If blue things are hitting red things, all the pressure, you can sort of understand, just leaks out because nothing's reflecting. But when red things are hitting red things, I didn't really illustrate in this thing, but there's got to be some way to illustrate the fact that it just keeps going back and forth, and the blue thing and the blue thing just keeps going back and forth. So redrawing the electrons, what's happening is the little blue bits can just keep going back and forth, back and forth. So you can understand that the closer two electrons get to it, so that, like I said, in brief, you can see this would cause the repulsion between electrons. Is the closer you bring them together, the more they're getting hit by each other. So this is essentially a higher pressure, and this frequency is higher than this frequency, right? I mean, this is frequency low, this is frequency high. And that's in essence, you can kind of get the idea that yes, these bits, these blue bits vibrating between the electrons, are the bits that are creating the frequency of what might be released as a photon. That is, these bits leaving, and they'll leave at a frequency dependent on how tight the relationship is to the electrons. So I've sort of indicated that you could explain something like an X-ray being released by an atom. So let's say you have, these electrons would be in arrangement to each other in some geometry where they're equal distant from each other, and say a force from the exterior, photons, come in and hit this electron. They'll compress, they'll end up pushing the electrons closer to each other than they like to be. So they'll compress the distance between two of these electrons. And depending on how they hit, that is, before this one can rebound, so if they hit fast enough, they'll push this electron deep, create high pressure, and that is the origin of, say, the release of a X-ray or something, because you're releasing stuff that is now compressed, and it's a higher frequency, it's higher pressure. So that's where the connection between frequency and energy, that's where it's created, is just in this circumstance where all you have to do is bring two things closer together and you make more energy. So it's like you're not making more little bits, all you're doing is moving two things closer to each other and you create more energy. And so this is really seen in like charged plates. I could take two charged plates and put 1,000 volts on them. Okay, so I have 1,000 volts of potential between them. One's negative 1,000, one's positive. And I move them together, and as I push them together, I'll increase, I have that correct, the voltage. Yeah. I'm trying to think whether it's, no, it's pulling them apart when they're, yeah, so as you pull them apart, you create more voltage. No. I shouldn't have made the comparison. I'm just saying there's a correlation between charged plates and what's happening with electrons in terms of the pressure being created, and the fact that as you push them together. Well, anyway, I'm got two concepts running through my head at the same time, and that's just getting me into trouble. So let's just get back to the basic function, which is frequency equals energy, but it only equals energy in the sense that if I move two electrons closer to each other, I create more pressure between them. It has a real consequence. Moving them closer to each other is something real is happening. I'm not just arbitrarily making them more repulsive. They're more repulsive for a reason. It's because they're sitting here, and the ping pong ball, so to speak, I can get to bounce back and forth, is bouncing at a much higher rate, and every time it hits, it's the same amount of hit. So in a moment of time, these things are getting hit by more things. And the whole basic theory is that there's obviously things from the environment hitting the other way, but the fact is if more things are hitting from this side than things hitting from this side, it's going to move, and so that's what moves things. So clearly, I'm just saying the point of this is just to point out that electrons being compressed, being forced to get closer to each other, will increase the frequency of the stuff bouncing between them, and the stuff bouncing between them, when it's released, ends up being a photon. So that's how photons are created. Photons aren't in the atoms. Well, photons aren't in the electron. Photons are what's between the electrons, and that's how they're released. Yeah. And what else is important there? So this gets into the whole idea of the expansion and contraction of energy levels in atoms. You know, say if you I don't believe in the standard model of electrons spinning around the nucleus and all that stuff, but let's just say there's an idea of the fact that they're collected in shells, and I would go with that. And you can just sort of understand it's the geometry. If I have 4 electrons in a shell and it's this big, there's going to be less energy in it than if I have 4 electrons in a shell this big, because now there's going to be more pressure between each one of the electrons. There's going to be a higher frequency of light you're capable of producing. So the more you compress an atom by creating high pressure, the more you compress those rings, the more likely it is you'll produce an X-ray, or you'll produce ultraviolet light, or some other non-standard form of radiation. Where when the atoms are in their natural configuration, you could also understand that natural is no wrong word to use. Their standard configuration has a rigidity. It doesn't like to be changed. And so that's like the spectrum you can read when you start to destroy atoms. When you burn them up, you release the energy that's in them, and the energy that's in them is usually in these standard packages of certain size. So it's only when you get into real high temperatures that you can actually compress the size of the atom, I suppose. But anyway, that's why each atom has a different spectrum, is because each atom technically has a different amount of these electrons, and that means there's a different amount of pressure holding them together, between them, repulsion. So it's the repulsion of the electrons that creates photons at a frequency. And that might be enough for this video as just an initial argument. So yes, photons are made of actual bits. What the bit's made out of, I don't care. Thickness in ether, I don't really. A lump in ether, I don't know. A lump of oatmeal in a sea of oatmeal, that doesn't really matter to me. The point is that they never destroyed. They're made, well, never destroyed. Okay, let's just understand. The argument is it's made of these quanta. Now, if we call the frequency the photon, clearly that can be destroyed. You can just you can create another thing in there and break the old frequency and have a new frequency. So you can change the frequency of a photon, or you can just basically annihilate it and break it into the little force bits, and they're still little force bits. They're still force. So you can just say the photon is doing this, and I can separate all three of those and have them move somewhere, and they're still force. They're just not in the electromagnetic spectrum of force anymore, and they're going to be realized as, well, if they're polarized, magnetism, and photons would be polarized. So when you break a photon, you turn it into essentially magnetism. Magnetism is basically gravity that's polarized. So a magnet basically just shoots out all blue ones out of one end and all red ones out of the other end. So they're proton, repulsive to protons comes out of one end, repulsive to electrons comes out of the other end. And that's all magnetism is. And then gravity is mixed polarizations, no segregation of the polarization, and no frequencies. So there's no consistent frequency, and the polarizations are mixed up. Reds and blues are in line with each other, that kind of thing. So it can't be read by an electron. See, if an electron gets hit by say you have a frequency, but the frequency is red, blue, red, blue, red, blue, the thing that receives it, the electron, would basically only get hit by the blue things. It would only reflect the blue things. And when the red thing came in, it would just throw it to the left. It would just throw it to the right, throw it up, throw it down. It would get rid of it. And that's a key difference. So gravity is full of photons. It's just they're not in the right arrangement to be detectable by electrons. Electrons can't detect them because they don't come at frequencies that the electron needs them to come at to tip the electron. And and then magnets, and so everything's just pressure, and photons are created by the pressure between electrons. They're in the pressure between electrons. So when two electrons are close to each other, they have photons between them, and the frequency of the photon that gets released is entirely dependent on how far apart the electrons are. Alright, that's probably enough of an assertion. So, and I would argue there's nothing in the experimental evidence that says this doesn't work as an explanation, as a mechanical explanation for how photons are created and how they function in the real universe, and the fact that, unlike what Maxwell did, see, Maxwell created equations that found out that gravity and magnetism moves at the same speed of light, and so then he turned, he said, okay, because it has the same speed, then light must be magnetism, a kind of magnetism, when it should have been the other argument. It should have been a recognition that the elemental bits are the same for both of these carriers. So the invisible carrier for magnetism, see, they have to call it a virtual thing because they don't account for the energy, because they don't say the universe is full of energy and that the magnet is a filter and it's just filtering energy coming from the external world. See, understand, magnets, there's no accounting. People don't account for those virtual photons. That's why they call them virtual. It's because there's no generator. They can't account for where the energy come from. When the sun makes photons, it has to use up energy to do it. But there's no accounting for the virtual photons that are emanating out of a magnet. They're not like the solar radiation in any way whatsoever, because they're not burning any matter or converting any energy. It's like magical energy. It's because they don't understand that the field is full of this energy, and all the magnet's doing is segregating it, shooting one kind out one way and shooting the other kind out the other way, and therefore strongly affecting electrons in one direction and strongly affecting protons in the other direction, separating the monopoles in the matter and polarizing it and turning it into a magnet. All quite simple. Alright, anyway, enough for volume 1, I'd say. And so till the next time, and future clarifications where necessary and such. Thank you very much. Your rational participation would be appreciated. But if you can't pull that off, then no bother.